Okay, so like Jeremy said, we're going to move down to the network layer now and talk about privacy at the network layer. So I'm going to present some ongoing work I'm doing with my advisor, Peter Steenkiste at CMU, and we're looking at measuring network privacy. So our goal is to measure how private a network architecture or protocol is. And before I tell you how we do this, I just want to spend a few minutes talking about the problem itself, because I think the problem space is just as interesting. So let's start with some preliminaries. So first of all, measuring privacy. Well, what do I mean by privacy? So for the purposes of this talk, I'm talking about three properties. So we're interested in, can the adversary learn who sent a packet? Can they learn who's receiving that packet? And can they link multiple flows from the same user? So essentially what we're interested in is, can the adversary figure out who you are, what you're doing, and build a history of your activity over time? Now I keep saying the adversary. I mean, we need a threat model here, right? So let's look at that. So unlike the standard sort of anything goes Dole-Vial model that we usually use to evaluate an encryption protocol or an authentication protocol, here for privacy analyses, most prior work assumes a global but passive adversary, okay? So the adversary can see all the traffic in the network, but they can't inject packets, drop packets, or modify packets. And now the last piece of the problem is what I call indicators, for lack of a better word. So these are the different sources of information that the adversary can use to try to break a user's privacy. And the three primary ones are packet headers, topology, and timing. So headers obviously leak information about where the packet came from and where it's going. But topology can do this as well, right? So an obvious example is if I'm sniffing the Wi-Fi in Starbucks, the packets I'm seeing are probably being sent by the people sitting in Starbucks with me. And then timing is important as well, especially if you're trying to analyze something like Tor. Now, these indicators turn out to be a really important topic, because the indicators that you choose to consider in your measurement tool have a big impact on what your tool can measure and how your tool operates. So these indicators, in a way, I like to think of them as sort of defining the solution space, or at least one dimension of the solution space for privacy measurement tools. Now there's an important difference between headers and the other two, okay? So headers and the way network devices like NATs and firewalls, et cetera, operate on those headers are fundamental to the architecture. They're properties of the design of your network architecture. And the other two, the traffic patterns and topology, are properties of an instance of that architecture, a particular deployed network, okay? So this means that if your tool looks at headers, what you're measuring is sort of the base level of privacy that's intrinsic to your architecture. And if your tool looks at topology and timing, what you're measuring is sort of starting at that base level, how much more do you lose based on the characteristics of your actual operational network, okay? And these are both important questions, right? So the privacy properties of an architecture are relevant to protocol designers, and the privacy properties of an actual operational network are relevant to the operators and to users who actually come and plug in and want to know, something about who's going to be able to see what they do. So not only does which indicators you look at affect what your tool can measure, but it impacts how you build your tool, the sorts of things that you need for your tool to work. So if you want to look at headers, well, you better have a model of headers and how devices interact with headers. And if you want to look at timing and topology, well, you need a network topology and you need a traffic matrix. Now, it turns out that a lot of previous work in privacy measurement, like these metrics that are based on, say, the entropy in the distribution in the anonymity set, are on the topology and timing side. And that's not necessarily surprising, right? Because a lot of these tools were designed to analyze Tor, and Tor is designed to make headers meaningless anyway, and so you're only left with topology and timing. So we want to start on the other side. We want to look at headers first, and there's a couple reasons we're doing that. So first, we want to do it because this side is less well explored, and we think that Tor is the sexy example, but in the base case, headers are the most obvious leak of privacy-sensitive information at the network layer. So we want to understand how to deal with that. And the second reason we want to look at this is because we actually do have interest in a tool that can measure the privacy properties of the design of an architecture. So the group I work with does a lot of work in future internet architecture, and so for us, a tool like that is really valuable. So in the rest of this talk, I'm going to present a technique that we call share count analysis. And these are sort of our first steps towards a privacy measurement methodology that looks at the information leaked by packet headers. Okay, so this is the high-level idea. Share count analysis sort of draws inspiration from header space analysis, which you might be familiar with. So the high-level idea is we're going to send test packets through models of network devices. These models manipulate the headers, and we track at each step in the network how much personal information are the headers leaking. And then at the end, we can sort of sum up everything the adversary was able to figure out across all its vantage points. So I'm just going to step through these three pieces and explain them briefly, and then wrap up with some open questions that we're looking at. So let me start with our model of network headers and the information that they leak. So because we want to be able to use this tool to look at different network architectures, we need a general model of a packet that's not specific to any one architecture like IP. So this is our general packet model, and there are three pieces to it. So the first are what we call meta fields. These are sort of, we've sort of abstracted out the generic privacy-related piece of information that a network header usually carries. So the four fields are the sender ID, the source network ID, the destination ID, and the flow ID. And so you can think of each of these sort of as like a bit mask over your actual packet header that just exposes the bits that are relevant to that particular entity. So let me show you an example. So if we're looking at TCP IP, the source IP address obviously identifies the sender. It also identifies the source network. The destination address clearly identifies the destination. And then all five of these, the standard 5 tuple, identify a flow. Okay? So for any architecture that you want to analyze with our tool, first you need to manually define these mappings, and then we understand how to sort of reason about your headers. And I'll explain how we use these fields in just a second. The second part of our packet model, and this is the most important part, are what we call share counts. Okay? So each meta field has a corresponding share count. And what a share count represents is the number of devices or the number of entities in the network that could possibly share the same value for that meta field right now. Okay, so picture me sending a packet like in my local network. The source IP address uniquely identifies me. So the sender share count would be 1. But say the packet leaves the local network, it crosses a NAT, and we swap the IP address for some public IP address. That source address just identifies the network, right? So when we cross the NAT, our sender share count increases to the number of hosts in the local network. And then finally, we model the payload just as an opaque value. We assume that application content is encrypted. And so the only thing the payload is good for is linking multiple sightings of the same packet. So let's say the adversary has a vantage point here and another vantage point over here, and a packet goes across the network. The headers might be changed in between those two vantage points by network devices. But if the packet payload is the same, we assume the adversary can link those two sightings, those two sets of headers, and combine any information it learns from both sets of headers. And I'll show you an example of that in just a minute. Okay, so this is our packet model. We have sort of abstract fields that relate to privacy, and then share counts, which represent how much the adversary knows or doesn't know about, say, who sent the packet or who's receiving the packet. So that's how we model headers and how much they leak. Next, we need a model of how devices manipulate those headers. So to define a device to use in our tool, you just need to write a short little spec block like this. This is sort of like pseudocode. And it defines two things. So in this example, I'm showing a NAT. And first, you need to define which fields it updates. And we don't actually track the actual values of these fields. We just keep a version number. And so if a device updates the field, we move it to version 2. And secondly, you need to define what are the new share counts. So if the device is updating header fields, the share counts might change. So you need to know what are the new share counts when a packet leaves this device. Okay, so this is the example I just described, right? So when a packet leaves a NAT, the sender share count becomes the number of hosts in the source network. So I represent that here with H sub n. Okay, so once we have a model of a header and a model of a device, we can make a path of devices and send a test packet through it and figure out how much information leaks to an adversary. So let me just walk through a very simple example of this that should sort of tie together these pieces. So let's say we have this simple path. We're sending through a NAT and then a Tor relay. Just pretend we have a single Tor relay in our path. And the adversary has a vantage point on each link. So the links are colored red to represent that. And we're going to start by forwarding a test packet. Okay? So in this example, I'm just going to describe how the sender share count changes. So that's the box in the lower left. And if what I say about that makes sense, the other share counts are being updated in a similar manner. So just pay attention to that box in the lower left. So again, when we send our packet, if someone is sniffing on this link immediately upstream of our sender, the sender share count is 1. So the source address in that packet is uniquely identifying who sent it. Once we cross the NAT, like I described, the sender share count increases to the number of hosts in the source network, because based just on the information in the headers, we can't differentiate among different hosts in the source network. And once we cross a Tor node, it increases again, because anyone in the internet can use Tor, and so when we see a packet leaving a Tor node, again, based just on header information, not timing, there's nothing in the packet that identifies who might have originally sent it. So the sender share count increases to H, the number of hosts in the internet. So now we're going to save a snapshot of this header state at each vantage point. So remember, each link was a vantage point, so we have a snapshot for each link. And now we're going to group, we group these into what I call linkable snapshots, right? So the first two snapshots have payload version 1, because the NAT didn't touch the payload. So the payload is identical on the first two links. And so the adversary can link those together and combine what it learns from both sets of headers. But the Tor node re-encrypted the packet body. So as far as the adversary is concerned, the third snapshot came from a different packet. We can't combine what we learned from that third snapshot with the first two. Now the way we sort of sum up what we learned is actually to take the minimum share counts we saw across all the snapshots in each group. So these minimum share counts sort of represent the most certain the adversary ever was about who sent the packet or where it was going. And now we can use these minimum share counts to sort of tell us what the adversary was able to figure out. So if I go back to the three properties I mentioned at the beginning of the talk, if we want to know if the adversary learned who the sender was, well, we just check, was the source network share count equal to 1? And if you're wondering why it says source network there and not sender, check the paper or ask me. Same thing with the receiver. If we want to know who's receiving the packet, we just check, okay, was the minimum destination share count equal to 1? And if we want to know if the adversary can link multiple flows from the same sender, we check, was the minimum sender share count and the minimum destination share count equal to 1? Now, it turns out share counts can actually tell us a little more than this, and I have a couple examples in the paper. I don't want to go into detail here, but just as a quick advertisement, we can ask questions like, test a bunch of different combinations of vantage points and return the smallest successful set for one of these particular attacks. And so that's maybe a rough approximation of the complexity or the amount of effort the adversary needs to go to mount one of these attacks. So clearly, if you have Tor nodes, you need more vantage points than if you just have a NAT. And secondly, we actually show an example of how we can use this to measure something other than privacy. So one of the examples we show in the paper is how we can use share counts to quantify a trade-off between accountability and privacy. Okay, so that's interesting as well, particularly for protocol designers. Okay, so that's a quick example of how we can use these share counts to test what leaks as we send a packet through the network. And this is the high-level idea. So first, we model packet headers and how much they leak. We model how devices manipulate those headers and change how much information is leaked. And then we have a mechanism to send a test packet and sum all this information up. Now, this is ongoing work. So we actually have a lot of open questions that we're thinking about now. So let me give you an example of a few of these. So first of all, we're interested in to what degree can this be automated? So I said that, okay, you have to manually define this mapping between your header fields and these meta fields. Could we get that from a packet trace maybe? Like could we figure out which bits identify the sender and which bits identify the receiver? So this is sort of a question of ease of use. We're also interested in, does our model actually capture all architectures? So I said we had this generic packet model so that you can plug in any protocol or architecture. But the question is, well, okay, could you design something that's so radically different that we just aren't general enough to capture it? So this is a question of generality. And then finally, we have two questions of sort of the completeness of the results of our tool. So I said that we assume the payload is encrypted and we only look at the headers. But that's actually not a perfect assumption because there are a lot of commonly used protocols that operate in the clear, right? So DNS is an obvious example of this. Another example is the TLS handshake. So you typically send the domain name you're trying to connect to along with a TLS handshake so that the server knows which certificate to return. And this is all sent in the clear before the encryption kicks in, right? So that's another source of information leakage that we'd like to take into account. And then finally, I said we're starting by just analyzing the architecture itself. We're just looking at headers, and we want to be able to say something about how good a protocol is in terms of privacy. But we're interested in expanding this over to the other side of that slide I showed you at the beginning and analyzing instances or deployments of an architecture as well. And so this means we need to know how to incorporate topology and timing information into the model. So that's all I have for you, and I'm looking forward to hearing your thoughts and questions during the panel. And with that, I'll turn it over to Tianlang.